So there's just a few questions asking you to choose a test and justify what you do with the results. So this is much more likely what you'd be asked to do. And the first one is ladybirds. And just looking at the data, we have got the years going up and the frequency of an allele. Some data for that as well. So you're correlating years against the frequency of the allele to see whether it goes up or down or stays the same. So with correlations, you're looking for associations, and so you'd be doing a Spearman's rank correlation. You're not going to calculate a mean here, or they don't fit into categories. So for this one, you'd be looking, it's an association. So is there a correlation? You'd be presumably plotting the year on the bottom and the frequency of the B allele there, and that appears to go up, then down, then up, down. It appears to be I wouldn't have thought there'd be a correlation there. The null hypothesis would be, so our null hypothesis would be there is no correlation between, and then say the things, year and the frequency of the B allele. You would do a Spearman's rank correlation, and you would calculate Spearman's rank, and if Spearman's rank is bigger than our critical value, then you can reject the null hypothesis. So there'd be less than 5% probability that the results are due to chance. So that's the first example that we can see. Then we've got another example. Fur seals living in our Antarctic seas. We've got years, and then we've got some data. So we would do very much the same thing. So instead of that frequency of the B allele, it would be number of adult fur seals, and that actually looks like it's going up like that. So that looks like a positive correlation. Here, the null hypothesis, you get used to doing the same thing. So year and number of adult fur seals. You'd calculate Spearman's rank and do exactly the same thing. That was quick. And question 3. You have got a young bird watcher who's watching a pair of tits breeding blue tits, bringing food back to the nest for some chicks. Very good. He measured return rate and got some data. So we are comparing the female and the male here and their return rates. Lots of data here. Presumably you would calculate a mean for these, and you would generate. So we would have the male and the female, and this would be the bird, and the return rate will be here in milligrams per hour, and these would who knows, but there'd be two bars there, and you'd be plotting the mean and looking at standard deviations. And so when you're doing that, what test are you using? So it's not a correlation. You're not looking at one as the other one changes. Differences between two means, yes. Chi-squared, do they fit into categories? No. We're not any expected ratios or anything like that. So it's going to be the student's t-test. So we'd be looking for, it would be calculating means, standard deviations, and then the statistical test that we're going to use is the student's t-test to calculate t. And you'd do that, and you'd be noting that your critical value would need n. So you'd go, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total n is 20. So your degrees of freedom would be, so your degrees of freedom would be 20 minus 2 is 18. You'd use a chart to get your critical value using that degrees of freedom. And you would have a null hypothesis. So your null hypothesis would be that there's no difference between these two. So null hypothesis, there is no difference, so no significant difference between, better put significant in there, between male and female return rates. And you'd be doing it if t is bigger than your critical value, then reject the null hypothesis, and in that case there will be less than 5% probability that results due to all the differences due to chance.